Okay, now we're going to talk about electric fields. Okay, now we're going to talk about electric fields. An electric field is really nothing more than the space around an electric charge where the force is felt. Similar to a gravitational field, which is the space around the mass where gravity is felt. Now, taking a look at the electric field lines, the field lines help give us some information about what's happening with it. Okay, what's the difference between those two? Obviously, direction. Our test charge is going to be a positive charge, so it's going to be the direction in which a positive charge would move. So, because like charges repel. So therefore the field lines go away from a positive and they go towards a negative. Now from a quantitative point of view, the electric field vector, which we use capital E for, is really force per unit charge. And we always use a positive test charge to figure it out. E is a vector quantity, so therefore direction matters. It's easiest to figure out direction using our rules of fact that like charges repel and unlike charges attract. Since E is equal to F over Q, the units of force are going to be newtons, the units of charge are going to be coulombs, so it's going to be newtons per coulomb. It also fits very well with the gravitational field. G, the acceleration due to gravity, is really a ratio of the force to the mass. Since we all have different forces and we all have different masses, but the ratios of those two are the same. Well, the same thing with electric field strength. So it is akin to the acceleration due to gravity. It's the force per charge. So therefore, if you had a bigger charge, it wouldn't necessarily have a bigger force. Okay, now, a charge of 3 microcoulombs causes a force of 800 newtons. What is the magnitude of the electric field? So E is equal to F over Q. F's 800 newtons, divided by 3 times 10 to the negative 6th coulombs. Well, 8 divided by 3 is 2.67 times 10 to the, let me think about this, how about 8th newtons per coulomb? And you can check my math. Okay, now we're looking at electric field lines between two separate charges, a positive charge and a negative charge. This is called an electric dipole. Notice how the charges go from the positive to the negative. So if I was a test charge right there, I would move along that line. So it's important to understand that a charge is going to go away from a positive and it's going to go towards a negative. So this charge out here would go away, then eventually it would be influenced enough to wrap all the way around there. It is very similar to the gravitational field pictures that we've seen of the Earth. Now here we have two positive charges, and you know if you have two positive charges, they're going to repel each other. The red net force vectors are showing you what would happen with the sum of both of those things, the sum of both of those charges, excuse me. So electric field lines can represent the strength and the direction of the electric field. So if I have a positive test charge and I'm going to have lines going away from it, what's going to happen is the fact that the closer they are, so the field is going to be strongest in this area because the lines are closer together. So the spacing represents the field strength. The electric field vectors would be tangent to any field line that's curved. So if I had a field line that did like this and curved, the electric field line at any point would be tangent to that line, tangent to that curve, like that. Now, one thing important to talk about with electric fields is what happens when we have conductors. In other words, what happens when we have something that will conduct electricity. So if I have something like this, and what's going to happen is if I have some type of electric field charge out here, it's not going to permeate into the center of the conductor. So inside it's 0. That's kind of nice. It shields it. And if there's any charge on some type of conductor, it will always reside on the surface. Electrons hate each other, so therefore they're going to go to the outermost skin. So if you're looking at a Van der Graaf's generator, the charges are equally on the outside of the charge. So if I have something like that, the charges are going to be right on the surface and they're going to be on the outside. Whether they're positive or negative, they're going to be on the outside. Excess charge is going to accumulate on sharp points. That's the reason that you can put a spoon in the microwave, but putting a fork in the microwave is not good. Don't even ask about a spork. Don't ever put a spork in the microwave. And electric field lines are going to meet the conductor perpendicular to the surface of the conductor. So if I had a positive charge over here, and then I had some type of metal thing over here, and if I was to look at the field lines would simply come into this. They would be perpendicular wherever they come in to that. And of course, if that's a metal sphere, they're going to reside on the surface of the sphere. Nothing gets inside that sphere. We use this in several different ways. The electric field is going to be 0 inside a charged conductor. It's the way we shield computer hard drives and stuff like that. We will put a metal cage around the outside of it that will shield it. So during a thunderstorm, would you be safer in a car or outdoors? Well, if you have a car that looks like that, and you're sitting in here, what's going to happen is any excess charge is going to build up on the outside. Since there's no field inside the car, you're perfectly safe. Get inside a metal object if possible when lightning's happening. By the same token, you're not going to get very good radio reception inside something that's steel. So therefore, sometimes steel buildings and mostly steel places oftentimes will not get a very good radio reception. Tunnels may be fine. It's metal that really causes the problem because it acts like, it does not have to be solid metal either. It can actually have holes in it and still work. Look at the screen of your microwave. The screen of your microwave has holes in it so you can see through it. It's not solid. Okay, how about a sample problem? Which field is stronger? Well, strength is directly related to how close the lines are, so therefore that one's going to be stronger. That could represent, if you think about it, from a gravitational point of view, that would be a bigger, more massive planet. This one could be Earth, and this one would be the Moon. Now, we're going to take a look at this equation right now. We've not talked about Coulomb's law. Well, we talked about it earlier, but we're going to go back through it again. E is equal to kq over r squared. Q is the central charge. Now we're talking about the electric field from a point charge. In order for there a force to be present, you have to have two charges. But a single charge will create an electric field. So now I'm going to move a test charge, and I'm going to move it 3 times farther. Well, E is equal to kq over r squared. And now I'm going to move it 3 times farther. 1 over 3 squared, 1/9. The inverse square law that we've seen show up several times. Okay, as always, it helps to sketch a little picture of what's going on. So if I had something like that, we'll put the 1 Coulomb charge over here plus 1c. We'll put the -3 Coulomb charge over here, separated by 2 meters. The point I'm worried about is right there. Okay, so now let's go ahead and attack and try to solve it. Remember, it's a vector quantity, so therefore we need to worry about the direction. Now, you can look at each one of them individually. If I put, remember, it's always based on a positive test charge. So if I put a test charge right here, and if I just look at the 1 Coulomb, I would get that. It's going to be repelled away from it. If I look from just the 3 Coulomb charges point of view, It's going to be like that. So what I need to do is calculate those two, and since they're since they're going in the same direction, you'd simply add them up. Okay, now let's take a minute and put some numbers in it. We know that E is equal to KQ over R squared. So K is 9 times 10 to the 9th newtons meters squared divided by coulomb squared. Excuse me, times 1 coulomb divided by 1 meter per squared. So if I get that, then I get an answer of 9 times 10 to the 9th newtons per coulomb. And again, that's going to the right. Okay, similarly, we're going to solve for the electric field strength for vector 3. It's 9 times 10 to the 9th newtons times meter squared divided by coulomb squared times 3 coulombs divided by 1 meter squared. So the answer is 27 times 10 to the 9th newtons per coulomb. We don't have to worry about the positive and the negative since we've already taken care of that in our thought process for the thinking of how the vectors are. So my total sum of the vectors is simply going to be the sum of those two individual ones. Remember, that's E1, that's E3. What I'm simply going to do now is add those up, and I get 36 times 10 to the 9th newtons per coulomb. Hope this helped.